So Ganesh, can you say this?
Yes, sir.
So without wasting the time, we'll proceed with yesterday's numerical. We had drawn the root locus for this numerical, and I will make a quick revision once we finish this numerical. So the next question was, what is the stability of the system, or what is the range of k for which system is stable? So we already know the root locus started from k equal to 0 at all the 3 poles, because it was a 3-pole system, and it proceeded to s equal to infinity as k tends to infinity. So same thing we can denote for all the 3 poles, 3 branches of root locus. So they all end at infinity, infinity, and other one is at third asymptote. It follows the third asymptote at minus infinity. So this is stable region. LHS is the stable region and RHS is the unstable region. So the system is conditionally stable. So we need to find till what range our system is stable. And third point, it is critically stable. Stable, unstable, critically stable. On the imaginary axis, we denote it as critically stable. So to find the condition for stability, let us find the value of k for which the system is critically stable. Okay, the point at which system is critically stable, and based on that we can mention the stability comment. So checking or finding k for critically stable is also same as finding k for which roots lie on the imaginary axis. So for what value of k your roots will jump to imaginary axis. Fine. So look at the root locus clearly. So the branches of root locus have moved like this, 3 branches in total, and we have plotted this graph for 1 plus g of s h of s function. So this root locus is for 1 plus g of s h of s function. So what modification we can make to find k? So we know that the closed loop characteristic equation is given by 1 plus g of s h of s. So for the given transfer function k divided by s into s plus 1 s plus 2, we get this polynomial s cube plus 3s square plus 2s plus k equal to 0. So this is the polynomial used for plotting the root locus. We varied k and we found out s1, s2, s3. Accordingly, we have plotted. So you will use this function and calculate for what value of k we get a pair of pure imaginary roots. So that will satisfy this condition. Okay, roots lying on the imaginary. So we'll find these points and the value of k for those points. So how to find that? So let us assume that those pair of pure imaginary roots as 0 plus or minus j omega. So two roots with 0 real part and only imaginary part. Where one root you can call it as just j omega, another root you can call it as minus j omega. And since this is third order, there exists third root also. But this is irrelevant for us now, because that third root is moving towards the leftmost side and it is in the stable region. So the remaining two roots I can assume as plus j omega minus j omega when they reach the imaginary axis. So this is a key point here. This is an assumption that when your two branches of root locus touches the imaginary axis, obviously the real part is 0. So only for that condition I can take the roots as plus and minus j omega, and now my task is to find what is the exact value of omega. So equation 1 is satisfied by one of the roots, obviously. So I will substitute one of the root in this equation as s equal to j omega and continue my evaluation. So since the root locus satisfies this equation, this root has also should satisfy this equation. So I'll substitute s equal to j omega here. It is j cube omega cube 3j square omega square plus 2j omega plus k equal to 0. I will separate out real and imaginary terms. So k is a constant, j square is minus 1. So the real part, 2 omega minus omega cube are the imaginary part. So j cube, I will take it as j into minus 1. So once you separate out real and imaginary parts, just equate them to 0. One equation is k minus 3 omega square equal to 0 because right hand side there is no imaginary term. And the other one also equal to 0 because there is no imaginary term. But we will get omega equal to plus or minus root 2 from the solution of this imaginary part. So therefore k equal to 3 omega square, and substituting omega here, we get 3 equal to 6. K equal to 6. So this means that when k is increased from 0 to 6, at exactly k equal to 6, the roots will come on the critical condition. Okay, the roots will come on the critical condition, and those roots are nothing but plus or minus j square root of 2, plus or minus square root of 2 into j. Okay, imaginary values. So if you make k equal to 6.0001, any value greater than 6, your root will jump to the right half of S plane. Therefore, system will become unstable after k increased beyond 6. So that is reflected here in the diagram as the point of intersection with imaginary axis as plus or minus j root 2. And the value of k for this particular point is 6. Okay, it is 6. So what I mean to say here is, if you solve by conventional method, suppose imagine we go by conventional method and I will start calculating all the three roots for different values of k starting from 0 to infinity. So when I start calculating S1, S2, S3 for say k equal to 0, I will definitely get those values as the poles of the system, the starting point. And similarly, when I proceed, say k equal to 0, 1, 2, 3, 4, 5, 6, at particular value of k equal to 6, my roots S1 will be plus j root 2, S2 will be minus j root 2, S3 will be some negative real value because one of the branch is moving like this. Okay, and when you increase k beyond 6, say 7, when you make k equal to 7, one of the root will have a positive real part, which is complex conjugate, and also it is in unstable region, and the third root will be in the stable region. So we have already studied, even if one of the root lies in the right half, the system is unstable. So from this we can conclude that for any value k lesser than 6, system is absolutely or asymptotically stable, or for any value k greater than 6, system is unstable. So that condition we have to mention here. The closed loop system is stable for k less than 6. Okay, the closed loop system is stable. That should be closed loop system is stable for k less than 6 only. So this is our final answer. So let me show that in a simulation. here I will type the transfer function. So in MATLAB, if you want to plot the root locus, you have to type the transfer function without k, because at the background it will by default consider the k, system gain k automatically. So I hope this is the given transfer function. And okay. So what happened to this? Yeah, this is the transfer function, and for this I will plot the root locus. Keyword is R locus, and G is our transfer function. So I will directly substitute the open loop transfer function, and I will get the root locus here as shown. So is it visible, Ganesh, the root locus?
Yes, sir. Yes, sir.
Okay. So here you can see this is 0, one of the pole represented with a small cross mark, another pole at -1, another pole at -2. Fine. So this is the actual root locus, and if you just click on any point, it will show you the gain at that point and the value of pole at that point. So in particular, if you follow the blue color line, it is that branch of the root locus which starts from 0. But when you solve numerical manually, we may not exactly get which branch is moving in which direction. So no need to worry about that. You just need to get the same shape of the diagram. No need to worry about which branch is moving in which direction. Okay. So if you draw the same shape with the same color pen, representing all the points correctly, then it is acceptable. So let me show you clearly. I will follow the blue line from here. So I am moving this cursor, and accordingly the gain is increasing, poles are changing. Okay, the poles are changing. Now they are complex in nature in this region. In this region, the poles were real. So gain is increasing, gain is increasing, gain is increasing, and on the imaginary axis, that is this 0 line, on the imaginary axis, what you can see is the pole has a very less magnitude for the real part. So it is as good as 0. Fine. So you can say it as 0 plus 1.4i, where 1.4 is approximately square root of 2. Approximately square root of 2. Fine. And the gain for this particular value of pole is 5.99, which is approximately 6. Okay. So as soon as I accelerate my bicycle, I can move in the stable region up to say 3 kilometers per hour, 4 kilometers per hour, 5 kilometers per hour. But at 6 kilometers, my bike is moving towards instability. After 6 kilometers per hour, your pole has a positive real part, which means you have moved to the right hand side of the S plane, which is unstable region. Okay. So at value k equal to 6, our third pole is in the stable region. Third pole is still in the stable region, but we have to look for the other other parameters also. At this value of gain, though one of the pole is in stable, others are in unstable. So whole system will become unstable. That is the conclusion. Any doubts with this diagram? Any doubts with this diagram? Yeah, you can ask. If anybody has any doubts, you can ask. I'll wait for a while.
Sir,
Yes.
can you show that point where the blue and the green line are almost meeting?
Yes, I will just zoom it. This is actually breakaway.
Yeah.
Yeah, so this is the breakaway. Fine.
Yes, sir. Like, sir, you were telling at that time it won't cut each other, so they're not meeting at that point.
They're not meeting. They're
Is it?
not meeting. See, what I mean to say is they're meeting at that point means both the roots will have same value.
Okay.
Is it possible to have same value for both the roots?
No, if we go by the statement that they will never overlap.
Yes, they will never overlap. Mean itself that they cannot have two values for the same value of gain. Okay, that is the whole idea. So therefore, this is breakaway. Okay, why it is selecting all other points? I don't know. So this is breakaway. It is not displaying value. Let me run the program again. Okay, now it is clear. So if I click at the junction, so it has some real value of minus 0.4. Minus 0.4. And if I still make it somewhat accurate, yeah, you can get it around minus 0.423. What was the breakaway point that we had got? Do you remember?
Minus 0.42. S is equal to minus 0.42.
Yeah, minus 0.43 approximately. At that point, there is a breakaway. So can you see the values clearly? I hope you can see it.
Yes, sir.
Fine. So that's it about the example of yesterday's class. We'll
Sir,
move on.
and
Yeah.
one doubt, sir. Sir, in the previous, like the previous class,
Hmm.
while you were talking about, there are two values of S, minus 0.42 and minus 1.58.
Yes.
So we took the minus 0.42 because there was an overlap on minus 1.58.
There is no overlap, no?
No, not in this, sir. S is equal to minus 1.58, the second case.
That we
So-
didn't take because that will get overlapped. Okay.
So
That
that
we
part
will
I don't
consider
know. How
as
will
a breakaway point.
Sir, but just like that, minus 2 will move this side. Oh, this green and blue, they will overlap.
Yeah, the green and blue, not green and blue. The other overlap I had shown. See, if you take breakaway here, it means you have to show something is breaking and following the asymptote. Fine.
Yeah.
If you take breakaway here, this has to break somewhere here, this has to break somewhere, and they have to follow asymptote. So two poles are following the asymptote, and the third pole which is left, it has to follow the third asymptote. Then only symmetricity is maintained. But symmetricity is not the only condition. While it follows the third asymptote, it will overlap here in this region with the other two branches. So that's why it wasn't possible. Got
So,
it?
but like here, the red one, it's going with the asymptote that falls in this side.
Left hand side, yeah.
Yeah. And
Yeah.
the green and blue are following this asymptote.
And the other remaining
from
two
the breakaway
asymptote.
point.
Okay.
Yeah. But 1.5 minus 1.52, that thing that you told that I didn't understand.
And let's see, we had got two breakaway points, and we are now in, we need to make a decision that which one should be breakaway. That was our intention.
Yeah.
Our objective, okay. So I chose first option as 0.42 and checked the condition, minus 0.4. So with this condition, there is no overlap and both the branches follow the asymptotes and there is even symmetricity obeyed.
Symmetry.
And the third one will follow third asymptote without any overlap.
Yeah.
But the same thing, if you consider here, there will be obviously some overlap. Okay, you just relook at last part of the previous video, you will get it sure.
Okay.
Okay.
Thank you.
Fine.
Yeah.
Okay. Anybody else has any doubts?
So that's overlapping with the asymptote. That's why we didn't consider, right?
Not overlapping with the asymptote, overlapping with one branch of the root locus with the other branch. That will never happen.
Okay, sir.
Asymptotes are just lines. See, in this diagram, I cannot show asymptote, but just I will show you. We had drawn three asymptotes, dotted lines, one asymptote here. So according to the definition of asymptote, it is just a straight line. Okay, it is just a straight line parallel to which your branch of root locus goes and meets at infinity. That infinity, I also don't know, you also don't know. Okay, but it is just a reference line, we can say in general. This is one asymptote and one branch is following that. parallel, not intersection. Second asymptote was at 300 degrees, so the second branch is following the second asymptote at 300 degrees, moves parallel and meets at infinity. Third asymptote was at minus 180 degrees. So 180 degree, though it starts from here, it is just a reference line for us. So we can directly show that the third branch will move at 180 degree, parallel to the third asymptote. Okay, so asymptotes are reference lines to give you a hint about shape of root locus. They are nothing to do with the root locus. Fine. So now what question he had asked is, if I take a other breakaway point, what is meant by overlapping and all? So overlapping is, I am speaking with respect to overlapping of root locus branches. See, rapid plotting is, that's what it is called as rapid plotting. Here you don't get a clear picture of where are the roots, because you are not calculating the roots for different values of k. So rapid plotting gives us some idea, hint only. Okay, hint only, and it reduces the burden of numerical calculation for every k. So for that reason, the three conditions should be taken care. I mean, without fail. The first one is branch of root locus will never overlap. And second one is the root locus is always symmetric about the real axis. So keeping in this condition, you try for any combination of root locus, any shape of root locus. Then ultimately, if you strictly follow this condition, you will end up with the right graph only. That is one convention we need to make in rapid plotting. But if you go by conventional method, that if you are very patient to make the calculation for roots for different values of k, then it will show you, that conventional method will show you at k equal to 0, first three roots are here. At k equal to 2, the roots, the blue color root will move here, and green color root will move here, red color root will move here. And at k equal to 4, still again the blue root will move here, green root will move here, and the third red root will move here. And at k equal to 6, the blue color branch will intersect with the imaginary axis, green color will also intersect with the imaginary axis, and red color will have some value here. So like that, it goes like that. Okay, have you understood? I think Mr. Abdul, you had asked a doubt. Are you convinced? Abdul?
Yes, sir.
Okay, so this numerical, I mean, this part of the control system is quite difficult initially. It comes by practice. So we solve 2-3 more numericals. It is very much, I'm very much sure that you will definitely follow it. Okay, so we'll move on to the next part. And I'll make a brief revision here, because one guy had raised a query yesterday. Like he is getting confused between open loop system and closed loop stability. So for that sake, I will revise again. Look at this write-up. We have open loop system, closed loop system. So open loop system is given by this transfer function that is well known to us. Suppose if we have something like this, transfer function something like this, 2 into s plus 5 divided by s plus 1 into s minus 2. So this is open loop system. So if I ask you a question, whether open loop system is stable or unstable, then straight away your job is to check the location of poles, okay, and directly you can answer me that question. So open loop open loop system is having an unstable pole at +2 or at the RHS of the S plane. So therefore it is unstable. And if I ask you the same question just by giving the open loop system or open loop transfer function, if I ask you closed loop stability, then you cannot give a direct comment for closed loop stability. You have to make some calculation, right? So you have to make some calculation for closed loop system. So what next? We'll write this closed loop transfer function assuming unity feedback. Then we'll make some calculation. And for that calculation, only this denominator is important for us for stability. Fine. So we'll find the roots of this denominator, then we will comment on the stability. So how to find the roots of this denominator? Substitute here 1 plus g of s h of s equated to 0. So you get s square minus s minus 2 plus 2s plus 10 equal to 0, and denominator goes to 0. So we have a square plus s plus 8 equal to 0 as the denominator. Then I will check the roots of this and I will calculate those values. One of the root is minus 0.5 plus 2.78j, other one is conjugate pair of that. So we have these two roots for a closed loop system. Okay, so we should look only for the real part for stability that I have already mentioned in one of the previous video, that if your real part lies in the left half, so it is stable, or right half means it is unstable. Fine, so let us see how it looks on the S plane. This is for closed loop. So minus 0.5 is the real part and 2.78 is the imaginary part, and these cross marks represent the exact location of poles. Fine. So this is LHS, this is RHS. So what is my comment on closed loop stability? The closed loop system is stable. So what is the key point here? So the key point is K you can take as a system gain. So K you can consider as a system gain, or K equal to 2 as a system gain. So this system gain can alter the stability in any fashion. Okay. So finally we write, if open loop system is unstable, then closed loop system may be stable or may not be stable, or may be unstable or may not be unstable. Everything depends on K factor, system gain K factor. Okay, everything systems on K factor. Okay. Suppose see you are standing in a bus stand, okay, waiting for a bus, and somebody suddenly comes with a Yamaha RX bike. Okay, and he is riding his bike only on one wheel, rear wheel, and suddenly you talk to your friend who is standing with you in bus stand, and you ask your friend a question. Hey, that guy is riding a bike. Do you think he will ride it with complete stability after 2-3 kilometers? Then your friend will answer, no, bro, it depends on what speed he will ride after 2-3 kilometers. It is as good as it depends on K only. So if he is riding in safe limit of K, it is stable. If he is not riding in a safe limit of K, it will be unstable. So open loop and closed loop stability will never be same. Will never be same in the sense they may or they may not be same, but in closed loop we have the factor K that will decide the stability. So got it? So if K is 2 here, we got some poles, but if K is 3, K is 4, obviously the values will change. So that's why we'll proceed with the analysis. So I hope the guy who had asked the question to me have understood this. So I think I cannot make much simpler than this. Please refer the previous videos without fail. Okay. So some key points we have to remember. Yeah. One who had asked about overlapping, you can look and compare these two diagrams. You can get this. Here there is no overlap, but here there is an overlap with the second breakaway option. Okay. Key point here is no branches of root locus. No branches of root locus will overlap. No branches of root locus will overlap. And the second key point is root locus is symmetrical, always symmetrical. Symmetrical And the third one is there always exist equal number of poles and zeros. Equal number of poles and zeros. So these are key points to remember, but nowhere it is mentioned technically. Okay, there exists equal number of poles and zeros. This I have underlined. I mean, the meaning of this zeros has a different interpretation. So let us just look at the present example. We had an open loop transfer function s k divided by s into s plus 1 into s plus 2. So there are three poles at 0, minus 1 and minus 2. Pardon, please correct that. There are three poles at minus 1, minus 2 and 0. And where are the zeros? Where are the zeros? Zeros are at infinity, infinity, infinity. Third one is at minus infinity. Because we say that our branches of root locuses are ending at infinity, which even I don't know and you also don't know. But we just say they are ending at infinity. That's why we say there exists equal number of poles and zeros. Equal number of zeros and poles, and if there is no finite number of zeros, they will end at infinity. That's what it means. So root locus starts from poles and root locus ends at infinite zeros. Fine. So if they ends at infinity, we call there exists a zero at infinity. That's it. So quickly we move on to the next numerical. Check the stability of the system or stability of closed loop system for the given loop transfer function g of s into h of s equal to k into s plus 2 divided by s into s plus 1. Also show that part of the root locus is circle. This is 10 to 12 mark question. Okay, 10 to 12 marks question. So quickly we'll start with the solution. There are two poles at minus 1 and 0. What I mean to say two poles means finite poles whose magnitude is finite. And there is only one 0 at minus 2, which means finite zeros. So I'll take this as capital P, this as capital letter Z. That is step 1. Step 2 is number of asymptotes. How many asymptotes? Any guesses? One asymptote, because P minus Z is 2 minus 1. There is only one asymptote. So what does only one asymptote mean? Okay, so it means there is one branch of root locus which will follow the asymptote and ends at infinity. Okay, so that branch of root locus do not have a 0 to end, therefore it has to end at infinity. At what is the angle of asymptote? So since P minus Z is equal to 1, according to this formula, 2q plus 1 divided by P minus Z into 180 degrees, q is 0, because only one asymptote. So when you substitute q equal to 0, you will get asymptote angle is 180 degree. And what is centroid? So we have to draw 180 degree line. You can still draw it, but centroid we will calculate for the sake of completion. So from summation of finite poles minus summation of finite zeros will become minus 1 minus 0 minus of minus 2 it should be. Yeah, minus of minus 2 divided by 1. So your answer is plus 1. So plus 1 on the S plane acts as a centroid. So let us see the initial diagram. So we have a centroid at +1. Yeah, it is centroid, it shouldn't be a pole. Then we have pole at 0, we have a pole at -1. Okay, this is centroid. Then pole at -1. Then a 0 at -2. 0 at -2. Then if you want to represent centroid, you draw 180-degree line. So this dotted line is a reference line for us to draw the root locus branch which ends at infinity. So how the branches starts, all those things we'll look into the next part. Okay. So the next step is to calculate breakaway and break-in point. So both breakaway and break-in are possible because we have a 0 here and 2 poles. Both breakaway and break-in are possible. So let us calculate those breakaway and break-in using the step I had mentioned. So calculate 1 plus k into s plus 2 divided by s into s plus 1, then rearrange this part. Take this on the multiplied with 1, then denominator will be multiplied by 0 on the RHS side. So take this on the RHS side, that will become minus s square plus s minus s divided by s plus 2. Simple algebra. Differentiate this with respect to s now. I'll take minus outside here, I'll keep it here. So dk by ds, differentiation. Keep s plus 2 as it is, differentiate this to s plus 1. Then keep this as it is, differentiate s plus 2, which is 1. Denominator equal to 0, so we have only the numerator. So after simplification, one can get the equation as s square plus 4s plus 2 equal to 0. Okay, the numerator polynomial is s square plus 4s plus 2 equal to 0. And s1 equal to what I have got as 0.172 or minus 3.414. Just check it once later because I doubt on this value of the root. Let me check it again. Between poles. Okay. Yeah, in my calculator I have got different value. So the value of s is something like this. S1 is minus 0.58, S2 is minus 3.414. Yeah. So this value minus 0.586 lies between the two poles. Lies between two poles. So the branches of root locus will meet here and then they will divide. So that should be the breakaway point without any doubt. 0.58. And as already discussed, break-in is between two zeros. So the other point is break-in without any doubt. But where does another zero come from is your question. We already have one finite zero, but there exists another zero at minus infinity. So the second point will come in between this finite and infinite zeros, therefore it is break-in point. Break-in point. So let us see how we can represent these things in the actual root locus. So after this step, as the initial stage of this chapter, it is quite difficult for you to guess the shape of root locus that I understand. Okay. So if you are not convinced yourself about the previous numerical or this numerical, okay, there is another way. Take your time and make a calculation using conventional method. You take the characteristic equation, you rearrange everything in terms of s, okay, s or s1 equal to s2 equal to s3 equal to, and for those equations you go on substituting k equal to 0, 1, 2, 3, 4, say up to 10 to 15 values. Okay, and for every S1, S2, S3, you go on marking in the S plane. Then later join all those points. Okay, you will definitely get this shape of root locus. There is no doubt. So that was the importance of conventional method which I had taught. You can do a kind of cross verification for yourself, but in rapid plotting, it comes by practice. So even if you are not able to understand how sir has drawn this shape of root locus, don't worry, give some time yourself. So with this information, let me draw the root locus. So we have a pole at 0, -1 and a 0 at -2. 0 at -2. And we have a centroid at +1. We have a breakaway point. We have a break-in point. And this is how I represent one of the branch. Breaks at breakaway and joins back at break-in. So this is how it proceeds as k increases. This is just approximation, no need to be accurate one. So since we got breakaway and break-in, we have to leave and come back. That is the only option. So this is a second branch. Which will move to -infinity. It follows the asymptote, you can say. This is actually asymptote follower. This pole has got a friend here, that's why it will stop. This pole hasn't got any friend, it will move to -infinity in search of his friend. So what is the comment on stability? Any comments on this stability for this numerical?
So critically stable.
Okay, anybody else?
Asymptotically stable.
Any condition here?
No, sir. Absolutely stable.
Okay, fine. Anybody else? Where is Mr. Hruday?
So I'm here.
What is the stability, Hruday?
Not sure, sir.
Not sure. Okay, Abdul.
Yes, sir. I told absolutely stable.
Okay, good. Told. Then Gopal.
Stable.
Not clear, huh?
Not clear, sir.
Okay, Saurabh Kumar. Saurabh Kumar. Tejas K. Nadim Sharif. Tejas K. What is your answer?
Sir, I'm not sure.
Not sure. Okay. Nadim Sharif.
Stable, sir.
Stable. Okay. Dipanshu Sharma.
Stable, sir.
Stable. Okay. Prakriti. Prakriti Iyengar.
Stable, sir.
Okay. Priya Y.
Sir, it's stable, sir.
Okay, fine. So this is actually a case of asymptotically stable. Okay, a case of asymptotically stable. It is not critically stable because whoever said it is critically stable, you definitely have looked at only this pole location, and you forgot that for k equal to 0, it is moving to stable region. Okay, but it is always better to mention clearly. I mean, don't just write the comment that this is asymptotically stable. Fine, but better mention for the safer side as the system is stable for k greater than 0. For k greater than 0, system is asymptotically stable. So this is a safe comment. Because obviously the system will be tested for k greater than 0 only. But someone may cross question you at k equal to 0, it has a pole at imaginary, what does that mean and all. So let us safer side mention it is stable only for k greater than 0, and k equal to 0, it is obviously critically stable. But no practical system is tested for its stability at gain equal to 0. That is other way of interpretation. So I hope it is clear. Anybody has any doubt with stability? Amog Mishra?
Not really, sir. I'll go through the lectures.
I'll go through like this, fine. Aditya Raj? Abhijit Sahu?
No doubt, sir. Understood.
Understood, okay, fine. Meenakshi L.
Understood, sir.
Supriya?
Yes, understood.
Okay. Supriya's voice is coming something like a remix song. Okay, that is fine. So we'll proceed with this. The second part of the question, show that part of the root locus is a circle. So show that part of the root locus is a circle is some hint they have given that it is a circle. I mean, it will definitely take a shape of circle. So this proof carries some important things which will be asked during interview and all. Some concepts are lying in this question. So let us see what is that concept. Let me take some water before proceeding. So this is very, very, very important. So the first point is we have plotted the root locus for the function or the condition of 1 plus g of s h of s equal to 0. So for this function or for this condition we have plotted. So we can also write this equation as g of s h of s equal to minus 1 plus j0. So I am making some addition here. If you take this 1 on the other side, it is minus 1. So what is 1 plus g of s h of s equal to 0? The conceptual meaning of this equation is any point on the root locus will satisfy this equation. Okay, or any point on the root locus will also satisfy this expression, complete expression. Fine. So plus j0 is to show that there is no imaginary term in the equation. Simple algebra. So next thing is I will write magnitude and phase angle for these minus 1 plus j0. So what is magnitude of this? It is minus 1 square plus 0 square equal to 1. So magnitude of this expression will be equal to 1. And what will be phase angle? It is g of s into h of s equal to tan inverse of, the real part is minus 1 now. Therefore, it lies in the which quadrant? Or which line? It lies in on the 180-degree line. So minus 1 on S plane is on 180-degree line. Therefore, the phase angle is 180 degree. This I have told already. Okay. You should look for the quadrant depending on the real and imaginary values. So based on this, I'll repeat this explanation again. So we plotted the root locus for the roots of characteristic equation. And the roots of the characteristic equation will be obviously given by this expression. So every root of the characteristic equation satisfies this expression. That is the ultimate meaning. So I'll make a small rearrangement, and in the numericals, they will give only the loop transfer function, that is g of s into h of s. So I will express every point on the root locus can also be given by this expression, which also means in terms of magnitude and phase angle equal to 1 and phase angle equal to 180 degree. So this magnitude and phase angle are coming into picture because we are dealing with a complex plane. We are dealing with a complex plane. Therefore, phase angle of g of s into h of s on the complex plane at every point of the root locus will have 180 degree phase angle. That's how you can interpret. These are the two conditions we can say that the root locus is drawn. So since every point on the root locus lies on the imaginary axis, lies on the imaginary plane, it should be, 1 second. Okay, sorry for this, there is one word mistake I have done. Every point lies on the imaginary plane, it should be. Please correct this later yourself. On the imaginary plane, we can say that every point is of the form a plus jb. A plus jb, fine. So in this complex plane or imaginary plane, better we call it as a complex plane, wherever you take a point, it can be written as a plus jb form. And if it lies on the real axis, it is only real value. If it lies on the imaginary axis, only imaginary value. But in general, it is a plus jb form. Any point on the complex plane. Therefore, what we can say that is, let S equal to sigma plus j omega. Let S equal to sigma plus j omega be a point which lies on the root locus. Which lies on the root locus, which is as good as a complex number. Fine. Which lies on the root locus in the sense you can substitute this value of S in any of these equations because it is in a complex plane. So there is no harm or no loss of generality in considering every point on root locus to be a complex number. Okay. These are little complicated. I feel your difficulty. See, what I mean to say is, you can locate any point on the branch of root locus with this fashion. Suppose imagine you are starting from the real axis, then obviously your imaginary value will be 0. But still, it governs the representation of that point. And if suppose the branches will deviate from the breakaway point, then the roots will start becoming complex conjugate. They obey this representation. So that's how we can say any point on the root locus can be in general represented as a complex number. Fine. So that satisfies the root locus. This representation means it satisfies the root locus. So let me put S plus j omega in g of s h of s. Okay, we already have a g of s h of s given by in the numerical. So I will substitute sigma plus j omega in that. So it will become g of s as d of sigma plus j omega h of sigma plus j omega equal to k into sigma plus j omega plus 2. This is s plus 2. Divide by, we have s, which is just sigma plus j omega, and s plus 1, which is sigma j omega plus 1. Fine. Okay. We have real terms here, sigma and 2, sigma and 1. In all three terms, we have real part and imaginary part. K is a constant, which is only real part with no imaginary term, imaginary part. So what I am going to do, our ultimate objective is to show that part of root locus is circle. Okay, part of root locus is circle, and for that we are doing a circus. And that circus is within given loop transfer function only. Okay, so what we discussed previously, I am putting it in one single sentence. Every root of the characteristic equation or every point on the root locus has to satisfy the angle condition. Angle condition. So what is angle condition? Which we had written earlier. That is, angle of g of s should be 180 degree. I will correct it. Plus 180 minus 180 are same, but okay, it is 180 degree. So we will apply that condition for the given loop transfer function. So what happens then equation 2 becomes angle of gh of j omega equals to, what is the angle of k? Angle is 0 by k, which is equal to 0. And what is the angle of other term? Tan inverse of imaginary by real part. It is omega divided by sigma plus 2 divided by tan inverse of omega by sigma, and the third term tan inverse of omega by sigma plus 1. The condition is should be equal to plus 180 degrees. Should be equal to plus 180 degrees. Anybody not understood these equations? Please revise your knowledge on complex numbers from basic electrical. So this is how we write the phase angle condition. So what is the next thing? We said that every point on the root locus satisfies this condition. So the points are taken in general, omega and sigma. So let me simplify this, and it will become, the denominator will take a negative sign when it goes to the numerator, which is equal to angle. Fine. So here I will just speak for 1 minute. Our objective is to show that part of the root locus is circle. And now we are proceeding with the idea that every point on the root locus obeys this condition, or every root of characteristic equation obeys this condition, where this sigma and j omega are set of points which are calculated over a range of k. So what I am going to do ultimately is, I will show that these set of points which are calculated from k will make a circle. That's why part of the root locus is circle. Right? So to show that, I have to do some algebra. I have to finally end up with some equation which looks like for a circle. That's our ultimate objective. So how to arrive at an equation of a circle? So I will simplify this expression using this trigonometric identity. I hope everyone is aware of this trigonometric identity, diploma students also. If not, please go through it. And also, tan of 180 is equal to 0. Oh, tan of 180 should be fine. So what next? Start simplifying. I have simplified for you, and you have to follow the same steps for the other numericals. So I'll consider first these two terms. So they will become tan plus tan when I take minus outside. So omega by delta plus omega, sorry, sigma plus omega by sigma plus 1, which is x plus y, and 1 minus multiplication of these two. Fine. So I'll simplify only the things in square bracket. It's omega delta plus omega and plus omega delta divided by delta square plus delta. So this denominator and this denominator will cancel. What we have finally is 2 omega delta plus omega and delta square plus del, oh, why I'm calling it as delta, sorry, sigma square plus sigma minus omega. 2 omega sigma plus omega plus sigma square plus sigma minus omega. Yeah, it is correct. Fine. So next I will add this term. So this is tan inverse minus tan inverse now. Tan inverse minus tan inverse. I will take this for a simplification. So this first term minus the second term, which is here. So look at the simplification. So this will get cancelled, equal to 0. Denominator will go to 0. We are left only with this numerator part. So omega is a common element everywhere. Let me cancel it. Oh, I have made a small mistake here. This should be omega square. This should be omega square. Yeah. So omega square here and omega square here. So this will become omega square into omega is omega cube. So what remains is omega square. And we finally can cancel all omegas in the equation. Common element. So what we have finally is sigma square plus sigma minus omega square minus 2 minus 4 sigma minus 2 or minus sigma minus 2 equal to 0. So plus sigma minus sigma will cancel. 2 sigma square, yeah. So minus 2 sigma square plus sigma square is minus sigma square minus omega square minus 4 sigma minus 2 equal to 0. So all are equal to plus. So sigma square plus 4 sigma, the real part in the plane, then omega square, the imaginary part of the plane, plus 2 equal to 0. So this in xy plane, if I write x square plus 4x plus y square plus 2 equal to 0, something like that. Okay, these are the parameters of that particular real and imaginary axis. So how we can show that this is a equation of circle now? So we have to convert this into an equation of circle with a small modification. With a small modification, as x plus a square plus y plus b square plus c square, where c square is radius and minus a minus b as center. Fine, this is the equation of circle. It's well known to everyone. So this modification is little difficult, but you can still do it. Sigma square plus 4 sigma plus sigma square, addition and deletion of 4. Sorry, that everyone have to do. Plus or minus 4. plus or minus 4, I have forgot to make it minus 4. So minus 4 plus 2 is minus 2. If you take it on the other side, this should be plus 2. So that is as good as writing as square root of 2 square. Sorry for that. I forgot to subtract minus 4 here. Please make a small correction. So ultimately we have come with the expression for circle. So this is therefore root locus is a circle with a radius of square root of 2 and a center of minus 2 and 0. Minus 2 and 0. Fine. So that's it for the today's class. So take one homework. Take one homework and try to get the root locus for this. Please take the transfer function g of s into h of s equal to k into s plus 3 into s plus 2 divided by s into s plus 1. Divide by s into s plus 1. And please prove that part of the root locus is circle for this. Okay, that's it for today's class. Thanks everyone, and please do refer the videos without fail. I wanted one extra class. Let me talk to your CR. Then I will arrange only one extra class, just one numerical. It may be for 1 hour. Today, tomorrow or day after tomorrow, I will let you know. So thank you everyone.